Thank you for your introduction. So our group receives research support from GE Healthcare. So as we all know, MR images are complex value. And if you look at the face images, you can see there are different sources. Some are more clinically relevant, such as chemical shift, flow, and susceptibility. Some are less relevant, such as field homogeneity and from coil. Now, it turns out all of these phase structures are important in reconstruction because we can actually utilize them to reduce errors and achieve higher resolution. Now, one example is the partial Fourier image reconstruction method, where we assume most of the phase are from field homogeneity and from coil. Now, if that's the case, then the phase is mostly smooth, and so we can actually achieve up to 2 times acceleration with almost the same resolution. Another example where we exploit structures in the phase is water-fat imaging. Here, again, we exploit smoothness of the field homogeneity to separate between water and fat. In flow imaging, we encode flow measurements in the phase. Now, because blood flow is incompressible, everything goes in, has to go out. It actually has to satisfy a condition called divergence-free condition. And so we can also exploit this condition to perform a more accurate flow reconstruction. So all of these are all examples of phase regularized reconstruction, where we utilize structures of the phase in reconstruction to get higher resolution and reduce errors. Now, there have been many existing works proposed for each of these applications. They're all very effective. Some extend to parallel imaging and compressed sensing. But one issue is that, in general, when you want to combine these methods, it's not as straightforward. And so the goal of this work is to develop a general reconstruction method that allows us to enforce arbitrary phase structures with these applications I've mentioned in mind. And the hope is that with this general framework, we can combine all these reconstruction methods together and get higher resolution and reduce errors. The way we're going to approach this problem is that we'll first formulate this problem as an inverse problem. And we'll also propose an alternative way of handling phase wraps. Instead of unwrapping before or during reconstruction, as in most existing methods, we'll propose a method called phase cycling. And I'll explain later. Great. So for concreteness, I'll illustrate our method through partial Fourier imaging. So the forward model here is that we have a magnitude and phase image. We multiply them in the complex image domain, go through sensitivity, Fourier transform, and observe partial case-space measurements. Now, from this forward model, we can get the following objective function, where we have the data consistency term and the regularization term. And here we split it between magnitude and phase so that we can perform phase constraints. So in this case, we'd like to enforce some smoothness constraint for partial Fourier imaging. So this objective is non-convex, but we can still try to optimize for it. Now, one way to do it is through alternating minimization. You first fix a phase estimate, optimize for magnitude, and then you switch, fix your magnitude, and solve for the phase. Now, if you alternate between these two many, many times, then it turns out this is guaranteed to converge to a stationary point. Now, if you do this in practice, what you find is that you can actually get terrible solutions. Now, here's a reconstruction result applied with partial Fourier, parallel imaging, and compressed sensing. And you can see there's a huge artifact right here, which corresponds to actually phase wraps in the phase estimate. And so that's not good. But why does this happen? Well, if you look at phase images with phase wrap, and then you take a slice out of it, you see that the phase wraps actually kind of appear like edges. And so if you try to enforce smoothness constraint or regularization, sure, you get rid of most of the noise and also artifacts, but you also create some error along the phase wraps. And so this is some error that you have for each iteration. But the problem is you're doing these iterations many, many times, and so these errors would accumulate at the same position over the iterations. Therefore, your reconstruction results would have these errors piled up. Now, ideally, you'd like to do phase unwrapping so you never get into this situation. But that's also hard because you're combining all these phase imaging methods, and also you like to do it before reconstruction, where you have a lot of artifacts and also noise. And so what can we do? Well, if you look at phase wraps, sure, it's hard to unwrap them, but it's actually pretty easy to shift them. And the way you can do it is to multiply in the complex domain with an arbitrary scalar, complex scalar. What this does is that it would add an offset to your phase, and so this would effectively shift the phase wrap. Now, different values would shift the phase wraps differently, and what this suggests is a scheme that's very similar to phase cycling in balanced SSFP or wavelet cycle spinning in wavelet denoising. And so instead of having the phase wraps at the same position in all the iterations, you would shift the phase wrap spatially in each iteration. Now what this means is that even though you have errors in each iteration, these errors won't accumulate at the same location. Instead, they will get spread out over spatially, and so you won't get these errors piled up. You can also formalize it and interpret this as a stochastic update of the following objective function, where we robustify the regularization term over the phase wraps. So if you apply this in practice, on the left you have the reconstruction without the phase cycling with these huge artifacts. With phase cycling, you basically get rid of it. Now, if you compare it with a state-of-the-art partial Fourier imaging method, you can see that this actually achieves less error, as pointed out by the red arrows. So that's nice. But what's better is that this method is very general. We're not exploiting any kind of domain-specific knowledge. And so we can very easily extend it to water-fed imaging and also flow imaging. Now, because of time, I won't be able to go into detail, but the high-level idea is that you can incorporate a general magnitude and a phase operator that would allow us to generalize to water-fed imaging and also flow imaging. So one thing we can do with it is doing partial Fourier image reconstruction and water-fed separation combined with compressed sensing and parallel imaging. So on the left, we have the state-of-the-art method applied on a fully sampled data set. And on the right, that's the proposed method applied on an almost 7 times accelerated K-space measurements. So all of these are retrospectively undersampled. And you can see visually they look quite similar. And this is simply using the proposed method without much modification or without phase unwrapping. Another method that we can perform, another application we can apply it to is on flow imaging. So it turns out in flow imaging, often what you have to do is that in flow imaging, because we're encoding using the first order gradient moment, the readout cannot be too long. Otherwise, you get a significant signal dephasing. And so what happens if you want to get high spatial resolution is that you would do a partial readout. Now, in conventional method, even with compressed sensing and parallel imaging, you cannot compensate for the partial Fourier factor. And that's because the flow measurements is in the phase, and so the phase is not smooth. But then using the proposed method, we can apply more advanced regularization, and in this case, we apply a divergence-free regularization term, which compensates, which accounts for the parallel Fourier factor, and this is the result. And so on the left, you can see L1E spirit, which has a slight blurring in the magnitude image. And on the right, you can see our result, which shows great sharpening. Now, the phase images for the velocity, you can also see that our proposed method reduces a lot of the incoherent artifacts. So in conclusion, we've proposed this general phase regularized image reconstruction methods that's applicable to partial Fourier, water-fed separation, and flow imaging. And this can be combined with parallel imaging and compressed sensing. The key feature of our reconstruction method is an alternative way of dealing with phase wraps. So instead of unwrapping them, we cycle them. Thank you.